In this video, we're going to design a complete industrial piping system from scratch inside AutoCAD Plant 3D. We'll start by creating a realistic reinforced concrete building with structural columns, beams, floor slabs, and even the concrete floor layer. This gives us a real construction environment, allowing us to see exactly where piping can be routed and where it can't. Once the building is ready, we'll place the process equipment, including storage tanks, pumps, and a bucket filter. Then we'll connect everything with piping while following practical engineering principles instead of simply drawing lines. Along the way, I'll explain valve placement, pipe supports, pressure gauges, vents, drains, and how to attach piping to the building structure. By the end of this tutorial, you'll have a complete industrial piping layout and, more importantly, you'll understand the engineering decisions behind every step. Instead of designing piping in empty space, we'll work inside a realistic industrial building, just like in an actual engineering project. I've already created the grid and marked all floor levels, so let's continue by detailing the concrete structure. I'll start by adding the column corbels that support the concrete beams. This will help you understand how precast concrete buildings are assembled and, more importantly, how the building structure affects pipe routing. Once the structural frame is complete, we'll start placing the process equipment and designing the piping system inside a realistic industrial building. Now I'll place the concrete beams on the column corbels. These beams support the floor slabs and define the available space for piping. Here's a quick photo of a real precast concrete structure. Notice how the beams are supported by the column corbels. This is the same structural concept I'm using in this project. Before we start routing the piping, I want to build a simplified concrete structure. I'm not designing the building itself, that's the civil engineer's job. In a real project, we work closely together to make sure the building fits the process equipment and allows enough space for piping. The structural model helps me identify where beams, columns, and floor slabs are located, so I can avoid clashes and choose practical pipe routes. When working on existing facilities, I often use the original structural drawings to create a simplified model. It doesn't need every detail, it just needs to be accurate enough to support efficient piping design. It's very helpful to understand how concrete buildings are constructed. Once you're familiar with the structural layout, you'll naturally leave enough space for beams and columns while routing your piping without constantly second-guessing yourself. Here's a quick reference photo from the internet showing two common types of precast concrete floor slabs: U-shaped slabs and plain concrete slabs. I've had projects where I created an overly simplified building model. Later, when routing the piping, I discovered clashes with beams and floor slab edges, which meant going back and reworking the layout. That's why I prefer spending a little extra time on the structural model at the beginning. It helps avoid costly changes later in the project. Here I'm adding U-shaped floor slabs, which are very common in industrial buildings. One advantage of this design is that pipes can often pass through the middle, where the slab thickness is the smallest. This gives you more flexibility when routing piping. I've created the slabs with sharp edges to keep the modeling simple. In reality, the edges are usually rounded, but that level of detail isn't necessary for our piping model. If a floor slab is crossed by one or a few pipes, it's common practice to cut circular openings around them, typically leaving about 100 millimeters of clearance on each side. However, if large equipment passes through the floor, a simple opening is usually not enough. In those cases, one or more floor slabs may need to be omitted or replaced with a different structural solution provided by the civil engineer. The concrete skeleton is now complete, so let's move on to adding the walls. In industrial projects, the walls are commonly made from precast concrete wall panels or insulated sandwich panels. For this model, I'll use concrete wall panels because they're widely used in modern industrial buildings. The concrete part is now complete, so we can move on to the process equipment. The goal of this project is to pump water from the storage tank on the first floor to another tank located on the third floor. I selected a vertical storage tank with support legs so it can be installed directly on the floor. One thing I've learned over the years is that not everything needs to be modeled. I only add details that have a purpose, whether it's for piping layout, clash detection, maintenance access, or a better understanding of the project. Adding unnecessary details takes more time, makes the model heavier, and usually doesn't improve the design. The default support legs looked a bit too small for this tank, so I made them larger. Now the proportions look much better. Before, it looked like a bodybuilder's skipping leg day. I spent about 2.5 hours creating this model and squeezed it down to just 30 minutes for you. Here's one piece of advice that will save you a lot of time. Don't just drop equipment somewhere in the model. Place it on the building grid or center line first, then move it by clean dimensions like 1 or 2 meters, not random distances like 5,234 millimeters. This simple habit will save you hours when routing pipes, creating orthographic drawings, and making future modifications. When placing equipment, always leave enough space for maintenance. As a general rule, I like to keep about 1 meter of clearance around the equipment whenever possible. It makes inspection, maintenance, and future modifications much easier. If you're working with a tall storage tank, don't forget about the top nozzles. They may require a maintenance platform or safe access for operators. Now I'm adding the second storage tank on the 3rd floor. This horizontal tank will receive the water pumped from the tank below. Those support legs don't look right. This is what happens when you're in a hurry. It's always worth taking an extra minute to adjust the dimensions properly instead of leaving something that doesn't look realistic. I'll speed this part up 8 times while I adjust all the support leg dimensions. I'm placing this tank using the same principles as before. Always leave enough space for maintenance, whenever possible. Since this side is next to a wall, I'm leaving a smaller clearance there and keeping more working space where maintenance access is actually needed. Horizontal tanks are a good option when building height is limited. They require more floor space but provide easier access to the top nozzles. Before fixing the final position, always think about piping, maintenance access, and future modifications. A few extra minutes now can save hours later. Now it's time to add the pumps. This time I'm using vertical pumps, which are widely used in industrial applications. They save floor space because the motor is mounted above the pump, giving them a much smaller footprint than horizontal pumps. I'll create the concrete foundation first because the pumps need to be raised slightly above the floor. This provides space for drains, vents, piping, and other components that are typically installed around the pump. I'm making the foundation about 50 millimeters wider than the pump on each side and 300 millimeters high. For now, these are just initial dimensions. I'll adjust the final height later to match the piping layout. Now I'm deciding where to place the pumps. We'll have 2 identical pumps, one operating and one on standby. This is a very common arrangement in industrial projects, providing redundancy in case the duty pump needs maintenance or fails. I'll place the pumps between the 2 tanks. This keeps the piping shorter, reduces the number of fittings, and results in a cleaner, more efficient layout. Another reason for placing the pumps here is that I can use the center column as a support for the piping. Now that the equipment is in place, I can adjust the nozzles to make pipe routing easier. Since I'm using ISO standards for this project, I'll set all tank nozzles to PN16. I'll use the same pressure class for the piping to keep the project consistent. The pump suction line will be DN100, while the discharge line will be DN80. It's common to use a larger suction pipe than the discharge pipe. The larger diameter helps reduce the flow velocity and pressure losses at the pump inlet, giving the pump better operating conditions and reducing the risk of cavitation. Here's one very useful tip for pipe routing. While drawing a pipe, hold Control and right-click to change the pipe compass orientation. This lets you rotate elbows and continue routing in the direction you need without interrupting your workflow. I use this shortcut all the time because it's much faster and more comfortable than changing the orientation manually. One thing I've noticed when working in a model with lots of solid objects is that AutoCAD keeps snapping to their center points. This can make pipe routing frustrating because the cursor constantly jumps to points you don't want. When that happens, I usually hide the solid models temporarily. It makes routing much smoother and helps me focus on the piping instead of fighting the object snaps. While editing the video, I noticed that the pump nozzle size was incorrect. Fortunately, I caught the mistake later and fixed it. Even after years of using Plant 3D, little things like this can still happen. Sometimes I measure the distances and route the pipes manually. It gives me full control over the layout, especially in tighter areas. When connecting two open pipes, I use the auto pipe feature. Sometimes it doesn't create the exact routing I want, but that's perfectly fine. I simply let it generate the connection first, and then adjust it afterward. Here are the available auto pipe routing options. I usually try a few different ones and choose the layout that best fits the project. My goal here is to keep both pipe routes as similar as possible. A simple, symmetrical layout usually means fewer fittings, fewer welded joints, and lower fabrication costs. The suction side is complete for now. Let's move on to the discharge piping. And here I noticed that I used the wrong nozzle size on the pump. In many pump designs, the pump nozzles are smaller than the connected piping. The pipe size is often increased immediately after the pump to reduce flow velocity and pressure losses in the system. I'll correct the nozzle sizes now before continuing with the routing. On the suction side, I'm using an eccentric reducer. This helps prevent air pockets from forming in the suction line, ensuring a smooth flow into the pump and reducing the risk of cavitation. On the discharge side, I'm using a concentric reducer. Air accumulation is generally not a concern there, so a concentric reducer is the standard choice. At this point, I considered lowering the pump foundation to better align the pumps with the piping. After looking at the overall layout, I decided to keep the original elevation because it works well and doesn't create any routing issues. I don't try to make everything perfect on the first attempt. I build the model step by step and refine it as the project develops. The pumps I'm using here are generic models. At this stage of the project, they're sufficient for developing the piping layout. Later, once the client selects the actual pump manufacturer and model, we can replace these with the manufacturer's 3D models. This allows us to verify the final dimensions, nozzle locations, and clearances before construction. I'm planning to run the pipe straight up alongside this column to the third floor. This gives me a convenient location for pipe supports while keeping the routing simple and well supported. Here's a practical pipe routing tip. Whenever possible, avoid routing pipes across walkways at floor level. Instead, route them near the ceiling, where they can usually be supported from the building structure, provided it's suitable for carrying the load. Keeping walkways clear improves accessibility, makes maintenance easier, and creates a safer working environment. One more practical tip: try to use as few components as possible. If you can achieve the same routing with fewer elbows and fittings, that's usually the better solution. Fewer components mean lower material costs, fewer welds, less pressure loss. Without a detailed building model, we wouldn't be able to see these clashes with the structural elements. Let's make a small adjustment to the pipe route and avoid the beams and floor slabs. Another routing tip: whenever possible, avoid running pipes through the middle of a room. I prefer routing them along walls or next to columns, provided the equipment layout allows it. This keeps the central area clear, makes the piping easier to support, and provides better access for operators and maintenance. Here the pipe runs vertically from the floor alongside the column, then continues along the wall before connecting directly to the tank nozzle. This routing keeps the pipe well supported and avoids unnecessary obstacles. Here I'm adding a nozzle on the top of the tank. Not every nozzle is defined at the beginning of a project. As the process design develops, additional connections may be required, so it's common to create new nozzles during the modeling stage. How do I connect the pipe to the nozzle? It's actually very simple. I use the disk command to measure the X and Y offsets, then move the pipe by those exact distances. Never move the pipe by eye. Using precise measurements gives you an accurate connection and keeps your model clean. I'm changing the pipe color to improve the visual clarity of the model. Whenever I rotate the 3D model like this, I'm inspecting the overall layout. I'm looking for clashes, awkward routing, or anything that just doesn't look right. A quick visual review often reveals issues that are easy to miss from a single viewpoint. While working on the layout, I decided to add one more piece of equipment, a basket filter. It's a common component in industrial piping systems, used to protect pumps and other equipment by removing larger particles from the fluid. Now we need to find a suitable location for the basket strainer. It should be installed after the tank and before the pumps. I'm also not happy with the support legs on this model, so I'll modify them to better match the overall design. A basket strainer is a simple but very important piece of equipment. Inside the housing is a removable perforated basket or mesh that traps larger particles while allowing the fluid to pass through. When the basket becomes dirty, the system is isolated, the cover is opened, the basket is removed, cleaned, and installed again. Its main purpose is to protect pumps, valves, and other downstream equipment from debris. From the outside, a basket strainer looks like a simple piece of equipment with two pipe connections. However, its installation requires some planning. Don't mount it too high. During maintenance, the basket has to be removed through the top cover, so it should remain within comfortable reach. Also, make sure the top cover isn't blocked by pipes or other equipment. Always leave enough clearance to remove the basket without dismantling the surrounding piping. Before placing any equipment, I always ask myself one question: how will someone maintain it? If the answer isn't obvious, the layout probably needs improvement. Try to imagine an operator standing next to the equipment. Can they reach the valves? Can they remove an instrument? Can they service the equipment without dismantling half of the piping? Thinking about these questions early leads to much better designs. This is one of my favorite parts of the design process. Every time I add a new piece of equipment, I need to find the best location for it and then think about the simplest and most practical pipe routing. At the same time, I always consider maintenance. The equipment should be easy to access, operate, and service without unnecessary obstacles. I'm shortening the support legs to keep the pipe elevation consistent with the pump suction line. This avoids unnecessary low points in the piping. Low pockets often require additional drain connections and can make draining the system more difficult, so I prefer to keep the pipe run as simple as possible. Here I noticed a 12 mm elevation mismatch between the nozzle and the pipe. Instead of adding unnecessary fittings, I'll simply lower the nozzle slightly to achieve a clean alignment. Let's straighten this pipe run. While inspecting the layout, I realized the basket strainer doesn't have enough maintenance clearance. Let's move the tank a little farther away to create more working space. When making changes like this, I try to avoid moving each component individually. Instead, I prefer selecting everything that should move together. It takes less effort, reduces the chance of mistakes, and keeps the layout consistent. Our pipe routing is now complete. The next important step is adding valves and other piping components. This is where the model becomes much closer to a real industrial installation. First, I'll add the isolation valves. To keep this tutorial simple, I'm using manual ball valves from the custom parts palette. Looking at the process from the beginning, every major piece of equipment should have isolation valves. The tank needs one, and each pump should have isolation valves on both the suction and discharge sides. This allows individual equipment to be isolated for maintenance without shutting down the entire system. In this tutorial, I'm using only manual valves, but many industrial valves are automated, The most common actuator types are pneumatic and electric. Pneumatic actuators use compressed air to open or close the valve. They are fast, reliable, and very common in process plants because compressed air is usually available throughout the facility. Electric actuators use an electric motor and gearbox. They don't require compressed air and are often used for remote operation or where slower, more precise movement is acceptable. Here's a practical tip about valve placement. Don't install valves where operators can't reach them comfortably. Whenever possible, place manual valves at a comfortable operating height. Around 1.2 meters above the floor is a common target in many facilities. Avoid placing valves too low, where people have to crouch or crawl, or too high, where a ladder is needed for routine operation. Another useful trick is to place a 3D worker model in your project. It gives you a quick visual check to see whether valves and equipment are comfortably reachable. Just make sure the worker model represents a realistic height. Mine is about 1.9 meters tall, so I use it only as a visual reference, not as a design standard. Getting back to the valves, if you're using butterfly valves, they are often installed directly on tank nozzles. Their compact face-to-face length helps save space and keeps the piping layout clean and simple. This valve sits on top of the horizontal tank. In a real project, I would add a maintenance platform here. Before moving on, I always take a few minutes to inspect the entire model. Another common valve type is the check valve. Unlike a manual valve, a check valve operates automatically. It allows the fluid to flow in only one direction and closes if the flow tries to reverse. Check valves are commonly installed on the discharge side of pumps. They prevent reverse flow when the pump stops, protecting the pump and reducing the risk of the system draining back through it. Check valves must be installed in the correct flow direction. In Plant 3D, it has arrow-shaped form that indicates the permitted flow direction. How do you know when the basket strainer is becoming clogged? A common solution is to install pressure gauges before and after the strainer. As debris builds up inside the basket, the pressure drop across the strainer increases. When the pressure difference becomes too high, it's a clear indication that the basket needs to be cleaned. For now, I'm only placing the pressure gauge connections. I'll add the actual pressure gauges later. Right now, I just want to reserve the correct locations on the piping. If you'd like to learn how to create pressure gauges and thermometers in Plant 3D, I've already made a dedicated tutorial covering the entire process in detail. Pumps are also commonly equipped with pressure gauges. A pressure gauge on the suction side shows the inlet pressure, while the gauge on the discharge side shows the outlet pressure. By comparing these readings, operators can quickly determine whether the pump is operating normally or if there are problems such as a clogged strainer, low suction pressure, or excessive pressure losses in the system. They are simple instruments, but they provide valuable information during both operation and troubleshooting. Every low point in the piping should be checked for drainage. When the system is drained, liquid collects in these low pockets and cannot flow out on its own. That's why drain connections are often installed at the lowest points. As you review your model, look for unnecessary low loops. Eliminating them not only simplifies the piping, but also reduces the number of drain connections you'll need. Here I'm adding a manual ball valve for the drain connection. Ball valves are a common choice because they provide full flow, are simple to operate, and seal reliably when closed. And as always, Plant 3D has given us another fantastic looking valve. Let's spend a minute fixing it, so it looks a bit more like a real industrial valve. Here I decided that flange connections would be unnecessary for the small drain valve, so I changed it to plain ends to keep the model simple. In a real project, however, small drain valves are often supplied with threaded connections, so always choose the end connection according to your project specification and the valve manufacturer's design. When I want to keep the model simple, I often use plain end valves in Plant 3D. However, in the valve description or specification, I indicate that the actual valve will have threaded ends. This keeps the model clean and easy to work with while still documenting the correct valve connection for the project. The pumps also need to be drained during maintenance. That's why I'm adding drain connections on the discharge side. These drain points allow the pump and the connected piping to be empty before maintenance, making the work safer and helping prevent spills when the equipment is opened. The drain isn't only for the pump itself. It also allows the connected section of piping to be empty before maintenance or repair. We've already talked about drains at the low points. Now let's look at the opposite situation. High points. Whenever the piping creates a high point, air can become trapped there. That's why vent connections are often installed at the highest points of the system. They allow air to be released during filling and operation, helping the system fill properly and preventing air pockets. A simple rule to remember is, low points need drains, high points need vents. While editing this video, I noticed one small mistake. The vent connection should normally be smaller than the drain connection. In this example, the drain is DN25, so I would typically use a DN20 vent. It's a minor detail, but it's a good reminder that reviewing your model often helps you catch small improvements, even after the main design is finished. Now let's move on to pipe supports. My advice is simple. Don't just support the pipes, also pay attention to heavy components and equipment nozzles. Good support placement protects the equipment and improves the long-term reliability of the piping system. Every pipe support needs something to support it. Think about the structural engineer who has to attach it to the building. That's why I like routing pipes near walls, columns, or under the ceiling. It makes supporting the piping much easier and avoids long, unsupported spans. The horizontal pipe is supported for now. We'll add the steel support structure later. Now let's move on to the vertical pipes. Just like horizontal piping, they also need proper support to transfer their weights safely to the building structure. For the vertical pipe, I'm using a riser support. This type of support is widely used for vertical piping because it transfers the pipe load to the supporting structure instead of the equipment. In this example, I'm supporting the pipe from one side, which is sufficient for the simple layout. Since we have a long vertical pipe run, I'll add additional supports at higher elevations. This helps distribute the load and keeps the pipe stable. These pipes don't carry a high-temperature fluid, so I don't need to consider significant thermal expansion. For hot process lines, however, support design becomes much more important because the pipe expands and contracts during operation. Some supports are designed to carry weight, while others are designed to guide the pipe or allow it to slide. This is one of my favorite pipe supports, a hanger support. It's simple, effective, and especially useful for piping located at higher elevations. As long as the building structure can carry the load, it's usually a very practical solution. From the structural side, this type of support is usually quite simple. The structural engineer only needs to provide a steel plate or embedded plate with a hole for the hanger rod. The rod is then secured with nuts and washers to support the piping. Another common support method is supporting pipes from structural columns. This is widely used in industrial plants, especially in pipe corridors. Large numbers of pipes are often routed alongside columns and supported on steel brackets or pipe racks in multiple levels. Using the building structure this way provides strong support, keeps walkways clear, and makes future maintenance much easier. I intentionally left the support beam a little longer to allow space for future piping. Planning for future expansion now can save a lot of time and modifications later. One important rule: never treat an equipment nozzle as a pipe support. Equipment nozzles are designed to connect the piping to the equipment, not to carry the weight of long pipe runs. If the piping isn't properly supported, its weight, together with the fluid, valves, insulation, and thermal loads, is transferred directly into the nozzle. That can lead to excessive stresses, leakage, damaged flanges, or even damage to the equipment itself. Always transfer the pipe loads into the building structure, not into the equipment. I'm not very happy with this support structure. It's more complicated than it needs to be, so I'll simplify it by using a single support leg instead. Now that we have one support design, we can reuse it for the other floor-mounted pipe supports. There's no need to create each one from scratch. Reusing the same support keeps the design consistent, saves time, and simplifies fabrication. Before placing a support, ask yourself one question: where will the load go? Now it's time to add the pressure gauges themselves. The gauge connections were already placed earlier, so now I'm simply installing the gauge heads onto those connections. I prepare this pressure gauge in advance by downloading it and converting it into a live component. That makes it quick and easy to reuse in future projects. Make sure to rotate the pressure gauges correctly. The dial should face the operator, not the wall, so it can be read easily during operation. A pressure gauge is read by the operator. A pressure transmitter sends the pressure value directly to the control system, where it can be displayed, recorded, or used for automatic process control. And that's our project complete. I hope this tutorial showed you that good piping design is more than just connecting pipes. Think about maintenance, supports, accessibility, and the people who will build and operate the plant. Thanks for watching. If you found this video helpful, consider subscribing, and I'll see you in the next Plant 3D tutorial.